Say, oh, recording, perfect. I was going to ask you whether you were recording this. I see you are, perfect.
Yeah. Yeah. So let's make, because people are streaming in, I can see how the numbers are increasing every second. So let's just give a few more seconds.
Have people been participating very heavily?
Yeah, it's amazing. So there are hundreds of people at every session. So I think it's a big success to do it in this manner. And we'll see what the future will bring. So probably some hybrid formats, people joining in from all over the world, and a lot of people also meeting in person, because this is, yeah, it's a unique experience to meet with everybody. You know. So I guess we could get started. Welcome to the second foundation lecture at our ISBA World Meeting. It's a big pleasure for me to chair this session and to introduce Alicia Carriquiry. She is Distinguished Professor and President's Chair in Statistics at Iowa State University. And Alicia is originally from Uruguay and moved to the US as a student, where she gained a double degree PhD in statistics and I think was animal sciences. And Alicia is a really great applied Bayesian statistician and has worked in areas that are relevant to society and the good of the public good. Her most cited paper is a JASA paper on nutrition. And Alicia is also the director of the Center for Statistics and Application in Forensic Science. And I think we will hear more about that work today. And she has collaborated with governments and agencies all around the world to improve health and nutrition. And in recognition of this engagement and these achievements, she has many awards. And I would like to mention a particular one award, which I think is very, very special. She is elected member of the National Academy of Medicine, one of the few women, as far as I've seen, and this is a great achievement. And as past ISBA president, I would also like to mention that Alicia is a really devoted, dedicated member of the society and has served as ISBA president in 2001. So Alicia, it's so wonderful to have you today talk about in this foundation lecture about CSI Bayes. So Alicia, the floor is yours.
I so appreciate the introduction, Sylvia. So without further ado, let me see if I can. You can see my screen?
We can see it fine, yeah.
All right. So, oops, sorry, I didn't mean to do that. Let me organize myself. Okay, then. Meet Mr. Keith Howard. Keith Howard was a sailor that was stationed in Newport News, Virginia in 1982, I believe it was, when a horrible crime was committed in the area. This person that was wearing a sailor's uniform broke into somebody's home, raped the wife, killed the husband, and in the commission of the crime, beat the wife on a leg and left some teeth marks. So long story short, Keith Howard ended up being the defendant in this case, but the wife testified that he had not been the assailant. His dentition didn't even match the marks on the woman's teeth, but nonetheless, he was convicted of this crime on account of the testimony of this forensic odontologist that said, with 100% certainty, Keith Howard was the person who committed this crime. So with that introduction, what I'm going to talk to you about a little bit today is mostly forensic science problems and how statisticians can help alleviate some of those problems. So let me start with a little background. So bite mark, forensic bite mark analysis can perhaps be called a junk science. And what do I mean by junk science? I mean that nobody has really studied whether this discipline is valid, is reliable, has reproducibility, meaning that two examiners faced with the same evidence would reach the same conclusion. And in fact, a few years ago, a couple of forensic odontologists set out to explore whether forensic bite mark analysis was a reproducible science. And so what they did is they collected images from past cases, and these were abrasion injuries. And they had 37 board-certified forensic odontologists that were willing to participate in the study. And what they did is they asked each one of those forensic odontologists to classify these injuries that they were looking at. And I'm going to show you a graph now that's a little busy, so don't try to look at the numbers. Bear with me and I'll walk you through it. So this is what the results look like. So the odontologists were asked to classify each one of those injuries into, for sure, it was made by a human dentition, and that's what we have in light blue here, or it was made perhaps by a human, but I'm not sure. That's the dark blue. It was an animal bite mark. That's the light green. And I have no idea. That's the dark green. And I should have said that each one of these horizontal bars here represents one of those 80-some images that were presented to the experts. And what you can see from here is that except for a couple of the bite marks at the very top here, or the marks at the very top here, there's just no agreement between the experts in terms of what they're seeing. So obviously, reproducibility is an important component of validity. Validity has not been demonstrated, yet this type of evidence is still admitted in court. And Keith Howard is not the only person that has been put in jail due to the testimony of some forensic odontologists. So unfortunately, bite mark analysis is not the only forensic discipline that is a little questionable in terms of science. In 2009, and as a result of many scandals that had happened in the late 90s and early 2000s involving latent print analysis, hair comparison analysis, and several other ad hoc disciplines, the National Academy of Sciences in the United States impaneled this committee to take a deep dive and look at all the forensic disciplines and see how well they were doing in terms of scientific foundations. And what the committee found was that with the exception of DNA forensic analysis and single donor forensic DNA analysis, most other forensic disciplines stood on very shaky science, and they do to this day. But the committee was particularly critical of what we call the pattern comparison disciplines. And those are things that you hear about every single day, like latent print analysis or firearm examination or ballistics, shoe and tire tread markings, bloodstain pattern analysis, handwriting, question documents analysis, and our good old friend, the bite marks. And so there has been some progress since this report came out, but definitely not enough, and I'll talk a little bit about that. Fun fact, this committee was co-chaired by Konstantin Gatsonis, one of our colleagues, and Karen Kafarar was also a member of this committee, so the profession was really well represented. So let me talk to you about what the main forensic problem is and what a statistical solution or answer to this problem might be. So when a crime is committed, there's many different questions that forensic scientists may ask, but one of them, and the most common one, I think, is what we call the question of source. So if you find two items, one on the crime scene and one on the suspect, can you say whether those two items have a common source? So for example, you might find this shoe print on a crime scene, and then you catch a suspect, and it so happens that the suspect has shoes that look like this, and you ask yourself, could this particular shoe have left this print at the crime scene? Now, that source question that I just posed is what we call a specific source question. There's also what we might call a common source question. For example, you might say, I found 2 bullets in 2 different crime scenes. Can I say whether these 2 bullets have a common but unknown source? Were they fired from the same gun, for example? And there's a lot of subtleties from a statistical point of view. I'm not going to get into them today. If you want to know more about that, you should read the work of my colleague Danica Ullman and my friend Chris Saunders up in South Dakota State University. They are the real experts in this particular topic. So we're statisticians, so how do we formalize this source question? And in most criminal justice systems, there's 2 positions, right? So there's a prosecutor that wants to put the bad guys in jail, and then there's the defense that wants to make sure everybody is accorded the due rights. And so you can think of this in terms of 2 competing hypotheses that are put forth. The prosecutor's hypothesis would say that the defendant is the source of the evidence you found at the crime scene, whereas the defense's hypothesis can be many things, but one of them is, in essence, that hypothesis is somebody else committed the crime. It was not my client. So in the 50s and 60s, there was already some work on this question. And mostly people address this as a hypothesis testing question in 2 steps. First, look at the crime scene, at the evidence found at the crime scene and the item found on the suspect, see whether there's a match. And then if there is a match, see whether that match is probative or significant, rare, if you will. But in 1977, Dennis Lindley came up with a much nicer response to this problem. He published this paper in Biometrica in 1977. That's a little jewel. And if you haven't read it, I strongly encourage you to go look for it and read it because it's really wonderful. And the solution that Lindley proposed is the one that, spoiler alert, we're still using to this day. So here's what Lindley said. He said, all right, imagine his setup was the following. He said, there's a crime scene and a window is broken in the commission of this crime, and you have a suspect. And so there's fragments you can obtain from the crime scene window, the broken window, and the suspect has fragments of glass on his clothing as well. So what we do is we take measurements X from the crime scene fragments and measurements Y from the fragments on the suspect. And then we know that those samples, take the mean, those sample means are distributed around some unknown means, theta 1 and theta 2. And Lindley derived some of his results using normality. Then he relaxed that assumptions. We don't need that. And so if we want to tie this to the hypotheses, the prosecution's and the defense's hypotheses that I just showed earlier, this would be, the prosecutor's hypothesis would lead you to test whether theta 1 and theta 2 are the same or equal to some common value theta. In other words, both samples of fragments have come from the same distribution of whatever it is you're measuring. In this case, it was refractive index of the glass, versus the defense's hypothesis that says, my guy's fragments do not come from that broken window. And so that's equivalent to the alternative that theta 1 is different from theta 2. And so we know how to look at the evidence and decide whether the evidence supports one or the other hypothesis. Typically what we do is we look at the difference between Y bar and X bar, and if that difference is small, then that suggests maybe that the prosecutor is correct. And Lindley said, not so fast, because if those refractive index values you're looking at are very common, so that every other window in that town has the same refractive index values, then this difference being small doesn't mean much, because you might find lots of differences being small, even if the fragments come from different windows in that case. So what you look at, he says, what you need is also to consider the rarity of those values. So if you observe a match and the values you're matching are really rare, then you are onto something. Then you really have something to celebrate. And he said, in order to look at this rarity, what we need to think about is the distribution of those source means, theta 1, theta 2, which he assumed were distributed with common mean mu and some between source tau square. So this is, so he said, he went on and he said, all right, so now what you can do is you can compute the odds in favor of same source given the data. And so you have the ratio of some suitable probability model for X bar and Y bar under the assumption that the fragments come from the same window over the probability of observing these two means under the opposite assumption that they come from different windows. So the numerator here is the probability of observing the evidence under the prosecutor's hypothesis, and the denominator is the probability of observing the evidence under the defense's hypothesis. So Lindley went ahead and worked out the expressions for the numerator and the denominator in this particular example that he was working with. And he came up with this ugly function for this ratio. But the ugly function is kind of very intuitive because this function depends on two terms. The first term is the usual closeness term, so the square distance between X bar and Y bar, and that tells us about the matching part. The second term that this ratio depends on is the distance between Z and mu. Now, Z here is the weighted average of X bar and Y bar. And so this square distance here tells you about the rarity. And so when this distance increases, the rarity of the match increases, and the more probative the evidence becomes. So what Lindley's contribution was to suggest that we use this one number summary. He called it a likelihood ratio. Depending on how you parameterize these two models, you could think about it as a Bayes factor, perhaps. But it doesn't matter. He called it a likelihood ratio. And this is the one number summary we now use to assess the weight of evidence in most cases. So before I move on, I have to tell you a personal story about Lindley that I was reminded of as I was preparing this talk. So this is a million years ago. We were in one of the Valencia meetings, and Lindley and I were talking about wine. And he said, on Sunday evenings, my wife Joan and I really like to enjoy a sip of this specific German dessert wine. He said, but it's getting so hard to get in the UK that we haven't been able to give ourselves that pleasure for a while now. Okay, so I happen to be married to a German. And so next time we went to Germany, I bought a couple of these bottles of this wine and sent them to Lindley. And there was radio silence. I didn't hear a thing for months. And then one day I get this long handwritten letter from Lindley. And what he had done to show his gratitude was he had read the papers I had published until then, and he had made all these wonderful constructive comments. And I was just floored. I gave him a couple of miserable bottles of wine, and he gave me this incredible gift of his expertise and his comments, and I forever appreciated that. Lindley unfortunately passed away in 2016 at the age of 90, so many of you probably didn't get a chance to meet him. He was one of those special people. I hope you guys, in particular the young ones, get an experience kind of like that because it marks you professionally for almost ever. Anyway, so let me move on to talk about this likelihood ratio approach when the data we have to work with are actually images. And what do I mean by images? Well, I already gave you a little bit of a glimpse. Oftentimes, what we find at crime scenes are things that can be represented by an image. For example, you might have a ransom note or a threatening note or a signature that you think is forged. Or you might have, we already saw this, a shoe print at the crime scene and to compare to an image from the suspect's shoe. Or perhaps, again, you have bullets like the one I showed you before, and you ask ourselves, we ask ourselves whether the markings on this bullet coincide with the markings that a specific gun might leave on ammunition when it is fired. And the state of the art here, these are all three examples of images, evidence that come in the form of images. There's many more. But the state of the art here is not very advanced, to be honest with you. So examiners at the moment mostly rely on a visual inspection of this type of evidence, perhaps with the aid of some instrumentation like a comparison microscope or so. But that's about the extent of it. And at the end of the day, they compare these two samples, these two items visually, and they issue an opinion in terms of a categorical conclusion that might be, this is a match, this is not a match, or it's an inconclusive. I cannot tell one way or the other. So at the end of the day, the categorical opinion or the categorical conclusion is subjective, and it relies on the experience and the training of the specific examiner. And I'm not saying that they get it wrong. Who knows how many times they get it wrong, because with that type of process, there is no way to estimate, for example, the number of times these examiners make a mistake. Actually, there is, but it hasn't been done. So what I'm going to talk about is what do we do when we find ourselves with evidence like this? Can we somehow come up with methods to quantify the similarity between two images and do some statistics on that? And that's where I'm going to next. So let me start with handwriting analysis. This is the work of a former PhD student of mine, Amy Crawford, and Nick Berry, who was also a student in our center. And they both graduated. They're happily employed by Berry Consultants. But most of what I'm going to talk about here is their work. So handwriting analysis has been admitted into court for years and years, for decades, really. And it can take on many different forms. So sometimes the examiner focuses on the frequency with which some words appear or turns in the language. What I'm going to talk about today is the shape of the writing. So I'm going to talk about things such as the slant of the writing of a person, the connectedness between the characters, the shape of the loops, and so on. And so at the end of the day, the goal is to estimate the posterior probability that a specific person may have been the author of a question document. We're not going to get quite there. We're going to talk about the posterior probability of observing certain evidence under the competing hypotheses, like I talked about before. The example I'm going to talk about is when we have a closed set of potential writers. Imagine, for example, an office setting where somebody finds a threatening note, there's a bomb in the bathroom, and you know that one of the writers has to be somebody in that particular building. And the question is, so the samples that you get are scanned images of handwriting. And the question is, how do you get from those scanned images to something you might call data that you can work with? And so there's many different ways of going about that. But the way we have developed at CSAFE is the following. So imagine you have a word, for example, CSAFE, like I'm showing up here. And what we have come up with is a set of rules that pretty well-defined rules to break this writing into graphical structures. And there's code that does that. It's called Handwriter, written in a mix of C and R. And you can see this particular word is going to be written, it's going to be broken where those nodes are. So the resulting graphs are shown below, and mostly they correspond to characters, but not always. You can see, for example, that this A was broken into two different graphs. And each one of those, if you look at these graphs, of course, now suddenly you have something you can chew on, because each of these graphs can be defined by their topology. And so the question that we asked ourselves is, can we identify writers by the type of graphs they produce? In other words, if we see certain types of graphs in certain types of graphs more characteristic of some writers than of others. And what do I mean by types of graph? Well, before I go there, let me tell you. So if you get let's suppose you have a paragraph. That's your sample document. In a paragraph, when you decompose it this way, you might end up with maybe 400 graphs, between 300 and 500 graphs. So that's a lot of graphs, and none of those are identical. So the question is, can we reduce the dimension of this problem somehow? So the first thing we thought about was clustering graphs. And so we said, all right, let's see whether we can group graphs before we do anything else with them in clusters of similar graphs. So we thought about a k-means algorithm for graphs because that's nice and flexible and dynamic. In order to implement such a thing, you need to have a means to estimate the distance between graphs and also to identify the center of a cluster, if you will. So the distance between graphs, there was some work done before we got started. There's something called the edit distance for graphs. We extended that, and because we wanted to add the edge attributes to this distance calculation. And this is a schematic of how you might compute the distance between this graph and this graph. And there's 3 steps you take. The first one is just kind of like an earth mover's distance. How long do you have to move one graph to put it on top of the other? And then this one has to do with the general shape of the graphs, the distance in terms of shape. And this has to do with the edge attributes component. And so once you add all 3 up, you get a distance between 2 graphs. All right. So what we did was we said, all right, let's get some data and let's see whether this works at all and where does this take us. So we assembled this large set of writing samples. The data, we got writing samples from our own database that we have generated, but also from a database called CVL that is maintained in Germany, and another one called IAM that is Austrian. And because we wanted a mix of different types of writers, and what we did was the following. We said, can we use this clustering approach to create a template that we can use later on to analyze new documents when they become available? So this is like training an algorithm, if you will. So we fixed the number of clusters at 40. We assembled this training data that I'm telling you about, and we created this template. And the template, the 40 clusters that we obtained for this particular training data set that I'm telling you about look like this. And each one of these little boxes, think of it as a bucket. So imagine you have these 40 buckets on your desk, and each one of these buckets contains a bunch of graphs that are similar but not identical. Each one of the buckets is best represented by this red graph, which we call the anchor or the exemplar. But there's variability among the graphs in the same bucket, and that's shown in the shading that you have over here. All right, so now that I have these buckets, what do? Well, let's suppose that I have a new document that I wish to examine. What I'm going to do is I am going to extract the graphs from the document, and then I'm going to take those graphs and put them in the corresponding buckets where they belong. And at the end of the day, what I can do is I can count the frequencies of graphs in each bucket and call that the data vector for the dth document produced by the wth writer. So that's my first piece of data, the frequencies with which the writer contributes graphs to each one of these clusters. We can extract more data to a document. And for example, we could think of the attributes of the graphs themselves. And so what I'm showing you here is 2 different writers and the graphs they contributed to one of the clusters. So this is the cluster that's anchored by this red graph. And these are 4 exemplars. These are 4 examples of graphs contributed by this particular writer to this particular cluster. Here's a different writer, and these are the graphs that this writer contributed to this cluster. So like you can see, there's variability between these 2 writers in the slant of these graphs. And so we thought, how can we capture the slant? What we did is we looked at each of these graphs on a 2-dimensional grid. we extracted the principal components, and then we looked at the angle of the first principal component with respect to the horizontal, converted that into polar coordinates, and what we get for each rider and each cluster is a figure like this. It's a distribution of angles like this. Angles live in a circle, so if you want to choose a probability model for these angles, you have to be careful. And what we picked was a Rapp-Cauchy model for the angles on the circle. And the Rapp-Cauchy distribution depends on two parameters, a location parameter and a concentration parameter. And you can see that these two riders are quite different in terms of the location. Well, I don't know about the location, but the concentration is definitely very different. This rider produces angles all over the place. This rider clumps all of their angles in this one area of the circle. Okay, then, so we have all kinds of data. So how would we model these data? So here's the setup. Suppose you have the closed set of riders that I was talking to you about before. So I have some number of riders, and I have several samples of writing from each one of those riders, and I have a question document. So what I'm going to do first is I am going to fit a model to characterize the writing of each one of those riders. And so I'll start. This is a busy slide again. I'll take it. I'll describe it in parts. Let me start with this first part. This is what the data might look like. The frequency data might look like. So you have a bunch of riders and a bunch of documents that were written by each rider. Each of the lines in your data set represents a rider by document combination. Each column here represents a cluster or one of those buckets. And so if you look at cluster 2, for example, you can see that these three riders that I show here have a lot of different, there's a lot of variability in terms of the rate with which they contribute graphs to cluster 2, cluster 3, cluster 4, etc. So what we did is we said, all right, let's pick a very simple model. And we picked a multinomial model for the vector of observations of frequencies for the D document by the W writer. And this multinomial model is indexed by a parameter vector pi, and which is specific for each writer. And the pi's then have a conjugate prior that's a Dirichlet, again, indexed by some parameter vector gamma. And the gammas we assumed are gamma with known hyperparameters A and B. And before you tell me I should have been, we should have put a hyperprior in A and B, we did. The results were pretty much the same. So I am just going to show you what we got from the simpler model. All right. For the angles, it's a little bit different. We have, first of all, we have a ton of angles because these angles are computed at the level of the graph within the cluster within the rider. And so there's thousands of these angles. And again, we decided to model them as Rapp-Cauchys. Mu is the location parameter, tau is this concentration parameter. For mu, we picked a conjugate prior, so another Rapp-Cauchy centered at eta sub k. So this is for each cluster, we have a different eta. And for the etas, we put a uniform on the circle. For the taus, we did something a little different because we were hoping that some of the taus, some of the clusters would fall off, meaning that some clusters would not be informative in terms of rider when looking at the slant of the graphs. But that did not end up being the case. And so the prior for the taus was a mixture of a beta and a point mass at 0. And this mixing parameter phi is has a Bernoulli distribution with probability theta k, and non-informative prior. Okay, so now suppose you have 100 writers in your closed set of writers. You fit this model, and each writer is going to get his or her own set of parameters. So now you get a question document. Let's suppose that the squirrels kidnap your dog and they send you a ransom note, and you want to know which one of those squirrels was the actual kidnapper. And so what you do is you take this question document, so you take this ransom note that this gentleman is holding, you extract the vector of frequencies and the vector of angles from the document. The writer for now is some unknown writer W star. And then you evaluate the posterior predictive distribution that you obtain for each writer in your closed set using the evidence or the data that you collected from the crime scene note. And so what you end up getting is, for each writer in the closed set, a probability of a posterior probability of observing this evidence conditional on this particular writer. And so I'm not going to go over the details here and the calculations. It's just a lot of busy work. But let me show you some of the results. So what we did is we assembled a different data set of handwritten samples from the same three sources, IAM, CVL, and CSAFE. This database had 90 writers, and each one had contributed at least 6 documents to the database. And so what we did is we used 5 of those documents from each writer to fit the model, and we held back 1 document so as to pretend we had a question document. So at the end of the day, we had 90 question documents, and what we wanted to do was compute so for each one of those 90 question documents, we computed Y star and Z star, and what we wanted to do was compute the probability of observing those values under the assumption that each one of the 90 writers had been the authors. And what we found was really very promising. So anything you see here on the diagonal is the correct answer. So the probability was highest when we were conditioning on the correct author, and everything in the off diagonal is a mistake. But if you use, let's say, point, so there's like 5 or 6 mistakes among the 90 cases. If you use 0.5 as the threshold for deciding mistake or not mistake, then we only had 4 mistakes in 90 question documents, which is pretty promising. So how do we do the likelihood ratio? How do we build a likelihood ratio in this particular example? Well, in this closed set scenario, the likelihood ratio is almost built in, if you will. So we have the evidence, and that's the information we get from the question documents. And then we can, and we have the probability models for the numerator and the denominator, which is where we just fitted. And so if the prosecution says it was W prime, we think W prime was the author of the note, what we can do is we can compute the odds of observing Y star and Z star under W prime in the numerator and all other writers in the denominator. So essentially what you end up doing is computing a lot of odds of observing the evidence for pairs WI, W2, second I, or II, whatever. Okay. So we're still working in that area, and we're moving in the direction of analyzing words, and it's getting really interesting. So I hope to report on that at some point later in the year or next year. So let me briefly touch upon footwear analysis. So we already spoke about footwear, and here's the same picture I showed you before. What you have here is a print that was found at the crime scene, and then you have the suspect's shoe. And first, before I go anywhere, notice that, this shoe sort of looks like it could have left this print. This is what we think that because this print and this shoe share what we call class characteristics. Class characteristics means that the 2 images appear to have been made by shoes that are of the same model, the same brand, the same size, perhaps. And so footwear examiners don't even bother doing any analysis if this looks like an Adidas print and this is a Nike shoe, obviously. So they only work in the cases where you have the same class characteristics. The suspect shoe is a plausible shoe for, it's a good candidate for this print. And that makes these comparisons very difficult because what you want to know is not, was this print made by a Nike shoe? What you want to know is, did this particular shoe leave this particular print? And so this is typically called the Q or question impression. This is called the known or reference impression. Okay, we call it. And if we find a way to measure the degree of similarity, I'm calling it E, between these two images, then we're in business, right? Because I can perhaps come up with a probability model to evaluate this evidence under the two competing hypotheses. I'm going to talk about same shoe, different shoe right now. Very convenient. So in forensic science, one thing you find is that there's very little data available for people to work on. And so one of the things we have done in CSAFE is spend a lot of money and a lot of effort in creating these huge databases that we put in the public domain. They are well curated, well documented, available to anybody. And for this particular study, we created, so what we did is we purchased 160 pairs of new shoes, Adidas, like the 80, about 80 were Adidas, like the one you see up here, and the other 80 were Nike Airflows, like the one you see down here. And we recruited 160 people that took the shoes with them, walked on them for about 6 months so that they could, we could get some wear and tear on the bottom of the shoes. And every 5 or 6 weeks, they would bring the shoes back into the lab and we would measure the daylights out of each shoe. And by that, I mean, we would get two-dimensional images using different technologies, three-dimensional images, high-resolution photography, you name it, we measured it. And so this and we did everything with 5 replicates every time. So this database is huge. It has about 33,000 images, I think. And if you would like to download it, you're more than welcome to do so. But be careful, it's huge. And so the results I'm going to show you today are those corresponding to the Nike Airflows and to one of the methods we use to obtain a two-dimensional image of the bottom of those shoes. And I'm going to use the data we obtained in the after 6 months of wear. And so the scanner we used has a resolution of about 300 ppi, meaning that each of these shoe images has anywhere between 10,000 and 20,000 pixels, which is a lot of pixels. And we were wondering whether we could reduce the dimension of the problem again. And this time what we chose to do was apply an image descriptor and extract interesting points. And so the one we used is this standard descriptor called SURF. This stands for Speeded Up Robust Features. And what this does is it identifies blobs of pixels, if you will, that are that may contain special information about that image. And so what we did is we extracted 500 of these features from each image of the shoe. And in order to, so the first, remember what the purpose is. The purpose is we want to see whether we can quantify the similarity between the shoes. And so in order to do that, we created pairs of images, 2 images, and there were 2 types. What we call the mated images and the non-mated images. The mated images are pairs of images that were made by the same shoe, that were obtained from the same shoe. And the non-mated images were pairs of images that were obtained from different shoes. But remember, all the shoes look more or less the same. So even the non-mated are pretty similar to each other. The first thing you need to do, or the first thing we had to do was align these pairs of images. And what we did is we used this idea from graph theory and computed the maximal clicks. And the maximal click is just the largest subgraph you can identify, you can find. And what we did was find the largest subgraphs in each one of the two images that were coincidental. In other words, the subset of those pixels that shared the same geometric arrangement. And so once we had that, we were in business, because now we can actually go about taking measurements. And so the measurements, the variables we measured that we used as proxies for similarity were three, and there's more you can think about, but we used these three. We used the size of the maximal click. We used the proportion of overlapping pixels, and here overlapping means in the same small neighborhood. And we use the median distance between those overlapping pixels. And you would expect that on mated images, the size of the maximal click would be larger, the proportion of overlapping pixels would be larger, and the median distance would be smaller. This is, by the way, the scanner that we use to obtain those photos, those data that I'm describing right now. So, okay, so we have three variables that we use to quantify similarity. And so we have these variables measured on each one of those pairs of images. And we have many pairs of images by the time you put together all the possible combinations. And so in principle, all we need to do is find a way to model those, that three-dimensional vector under the two, using the data from the two types of pairs of images. And if we can do that, then we should be able to construct a likelihood ratio. And so what do these data look like? So what I'm showing you here is for this particular example, these 80 pairs of Nike shoes. And these are the three similarity variables in the log scale. So the first one here is the log click size. This is the log median distance, and this is the log over percent overlapping points. The green here shows the values of those variables for the non-mated images, and the orange here shows the values of those variables for the mated images. And so what you can see is pretty promising, right? So there seems to be a lot of information about source in this data. There's some overlap between the values of these variables, but not a whole lot. And so, but none of these variables by themselves appear to be informative enough. So obviously you have to take all three into account. So you have to work with all three in a multivariate way. The other thing that we see is that even after conditioning on source, there's still some correlation between these variables. And so I'm not going to show you anything more about this, but in principle, if we get good estimates of these two densities, then we can construct a likelihood ratio. And given a new pair of images that produce values x tilde for these three variables, we can evaluate this likelihood ratio and decide whether those two images are more likely to indicate same source than different source. Okay, so the other way to look at this is as a classification problem, and this is where we started, actually, to be honest. And the question you ask yourself is, can we, instead of working with the three similarity variables, compute a univariate similarity score, if you will? And this would, in this particular case, it may not matter much, but in some cases you may have 20 variables that you wish to use to build a score. And so the way we went about this is by fitting a random forest to the data we have and constructing the score that I'm going to call G of X. So for those data, how did this score work? Well, like a charm, to be honest with you. This is the ROC curve. And this, the green here is the ROC curve for the random forest classifier. And you can see that it really does work extraordinarily well. The orange, by the way, is where we obtained when the classifier consisted of using just the percent overlapping points to determine class. It also worked pretty well. So the results were really excellent. The estimated, the equal error rate was under 3%, so woohoo. But the question is, how do we go about computing a likelihood ratio? So now what we have is not the actual measurements, but functions of the measurements, G of X. And we can certainly find a good probability model for G of X. But is this score-based likelihood ratio equivalent to the likelihood ratio that we would have obtained by basing it on the actual measurements rather than on a summary of the measurements? And the jury is out on this question. This is a hot topic in forensic statistics right now. There's some papers, there's some authors that have shown that, in fact, you can construct examples where the score-based likelihood ratio and the likelihood ratio are not only different, but directionally different, meaning one would support the prosecutor's hypothesis and the other one would support the defense's hypothesis. And that's, of course, the stuff of nightmares, where we have done some work in CSAFE on this topic. And we have found that the news are not so bad. It is true that things can go off the rail, in fact, in terms of directional differences, but the probability of that happening is so remote as to be close to zero. And in fact, in general, we find that the use of the score-based likelihood ratio cannot be poo-pooed. So this is more to come at some point. I won't say much more about that now. The last slide I have for shoes here is the following. So this, I kind of cheated because the wonderful results I showed you are unrealistic. So the images that I used, both of those images were of pretty good quality. And in real casework, one of the images is typically very corrupted or degraded. And there is no database of crime scene shoe impressions for which you know ground truth. And so we're in the process of constructing one. But in the meantime, what we did is we mimicked degradation of the crime scene image as follows. We took every shoe again and now imaged every shoe, but now putting 10 pieces of paper between the scanning surface and the bottom of the shoe. And not only did we do that, what we did was deleted most of the pictures. So we only ended up with these partially observed blurry print of the crime scene image. And we repeated the same analysis I showed you before. And these are now the values of those three similarity variables. And as you might imagine, there's some, obviously we lost information when we blurred one of the images, but there's still some things to work with here. And in fact, if you look at the ROC curves, you find that the random forest score is still pretty reasonable in terms of classification accuracy. For this example, the equal error rate was about 10%, which is still pretty decent in this area. So I'll leave you with a few parting thoughts. I hope there's many other things I could have discussed with you today. There's a lot of work that still needs to be done, and much of it hasn't even been started yet. And I hope to have conveyed to you that this is really interesting work. It's challenging. The statistical problems are endless, and the most important thing, I think, for me is that this is work that has an immediate and very important social impact. So you can really make a difference if you work in this area. So I'm calling on all of you to take an interest in forensic statistics and see what you can contribute. The sky's the limit, I think. And if you're interested, go to our website, because we have a lot of resources that we put in the public domain that anybody can access. We have a lot of databases. We have on all types of evidence. We have code that I would love for you to download, play with, and tell us how to improve. We have presentations, papers, you name it, it's on that website. So take a peek and dive in. And so let me circle back to Keith Howard. He was convicted when he was 26 of this crime and spent the next 34 years in jail for the crime that he really had not committed. And in 2016, finally, with the help of DNA analysis, the Innocence Project managed to get him exonerated. He has been having the time of his life since then. But he purchased an RV and has a significant other, and they have been spending their days living life and running around the United States, getting to see all the things he had missed during these 34 years. Unfortunately, Keith Howard is not the only person that has spent decades behind bars for a crime they hadn't committed. This is a collage of individuals. I got this from the website of the Innocence Project. These are all exonerees. And every single one of these spent many, many years in jail, wrongfully convicted of crimes. And you see these people come in all colors, they come in all age brackets, they come in all genders, and it is a crying shame that anybody should go through this. And so I have hopes that us as statisticians can contribute to reducing the probability that somebody will spend half of their life in jail because of junky science that's presented in court. So without further ado, I really wish to thank the organizing committee, the scientific committee, the committee that had worked so hard to organize the meeting in China. I wish we were in China. I hope you realize that inviting me to give this talk was the honor of a lifetime for me. And I was so happy to receive this invitation. So thank you from the bottom of my heart. And if there's questions, I'll be happy to take them.
So thank you, Alicia, for a really, really great talk and this insight how to use Bayesian methods. How to use Bayesian methods in forensic science and really make a difference in society and to these wrongfully convicted people. So we do have a number of questions. So I don't know whether you can see them or should I read them to you?
I see a couple.
I should read them. Why do you use k-means where k-methods might be an easier clustering algorithm for graphs?
Why do I use k-means instead of what again? I didn't get it.
Should I read it again?
Yes.
Yeah, sorry. Why do you use k-means where k-methods might be an easier clustering algorithm for graphs?
True. I think that was the first thing we tried and it worked, so we stayed with it. But maybe it's worth a second look. Thank you for the suggestion. There was no good reason. We were just looking for an alternative to doing what was being done at the moment, which was clustering graphs solely based on adjacency matrices. This is what the state of the art was at the moment. And we thought, these adjacency matrices are too, they don't have enough flexibility. So let's try something that we know is more flexible. So that was the reasoning.
Yeah. So then we have, what approach software do you use to do your graphical model inference?
What software do we use?
Software.
We use mostly R, to be honest with you, and a little Python and a little C, but the bulk of the code that we write is in R, and you need to understand that I live in the same department that Heike Hoffman lives, and if I did anything other than R, she would probably slap me.
And then we have question in the Q&R. So thank you for a wonderful lecture, Alicia. Extension to Lindley's reasoning, perhaps comparing the distribution of X and Y instead of just comparing the means X bar and Y bar could provide some additional information too. Any thoughts on this?
Yes, absolutely. I mean, this was the example. I just used the same example that Lindley was using in his paper. But in general, you would not compare the means. You would compare the actual observation. You would fit a distribution to the actual observations or to some subset of the observations, like we do with the shoes, where we look at the SERPs, at the features. Yeah, I agree.
Yeah, and then we have a great question from David Russels concerning the Lindley paradox, of course.
Of course.
But let me read it. Bayes factors are known to favor the simpler hypothesis, Occam's razor. In the forensic setting, the simpler hypothesis, less parameter, is that both pieces of evidence have a common source. It has possibly incriminate an innocent defendant. Is this an issue, or maybe I'm missing something? A great question.
That is a great question. So this is true, actually. And what has to be, when, computing these likelihood ratios of Bayes factors in practice is really an issue. I mean, let me start by saying that none of this stuff has been implemented in practice, except in the case of DNA evidence. But this point that, I don't know who it was, brings is one of those issues that people worry about. And so oftentimes what you see is that instead of constructing this ratio using Bayes factor, people use simpler approaches like a likelihood ratio rather than a Bayes factor itself to avoid this type of problems. Yeah.
So I think we have one more question here. Yeah. How easy is it to explain these methods to the court if you were an expert witness? It's a great question also.
It is horribly difficult. So we try very hard. So a big chunk of CSAFE's research program is dedicated to finding ways to communicate effectively with lay people and juries. We do a lot of training. So we have courses for judges and for lawyers on both sides, so that we can at least create some sort of common language. But the problem, of course, in the United States is that you have juries of your peers, and and the studies we have done that try to see what is it that people understand when you talk about likelihood ratios want to make you pull your hair out. And so you find people that say 1/10 is smaller than 1/100 because 10 is smaller than 100. And you want to kill yourself thinking that these are the people that are deciding on somebody's guilt or innocence based on the evidence that they are presented. So yes, communicating these issues is really not trivial, but there's a lot of research that's ongoing in that area.
Okay, so I'm getting warning. We have to terminate the session. Now, comments are streaming in like great talk, thanks, brilliant talk. So thank you so much, Alicia, for this great presentation. And thanks to everybody for joining, and have a nice evening, midday, morning, wherever you are, and see you at the upcoming keynote lecture. So thank you so much. Thank you.
Thank you, everybody. It was great to see everybody, or it would have been great to see everybody.
Ciao. Okay, so.